K, not the covariance matrix. And he argued that structure in X, in the axis, can be defined by imposing 0 constraints on the elements of K, right? And what I gave you here is the full definition of a Gaussian graphical model. So my model parameters are those elements of K that are not constrained to 0. K must be positive definite then, and also obey these constraints, right? So here, see, the absence of an edge again relates to conditional independence of the corresponding two variables, right? So that is precisely the type of model I want to think of for this level, right? And let's pay attention to this parametrization, you see. So the elements of K are not variation independent, right? You cannot just change one element and expect that is not constrained to 0 and expect things to still be fine, that is still get a matrix K that is valid, right? So that's the difficulty of the problem, right? So you have to live in this cone that corresponds to every particular graph, right? So that is the parametrization of our model. And, well, hundreds of papers have been written about doing inference in Gaussian graphical models, right? And you can think about maximum likelihood estimation, asymptotic results related to that, regularization, Bayesian techniques, and so on, right? Now, in parallel, there was this other body of literature that has been used extensively in epidemiology. So in this context, you see, I will just skip to the next slide. The graph, the spatial graph, doesn't really appear like this, you see, like the graph we have been looking at. In this context, the graph appears as neighbors of each state, right? So that's how the models, the spatial epidemiological models actually use this graph. So it says, well, what I know are the neighbors of each state, right? Clearly, those two definitions are equivalent, right? But there's a fine statistical constraint that comes out of that. That is, you create a much harder problem for yourself. Why? Well, before we look at this equation, right, we can just think what's happening if we have, say, the conditional of x given y and y given x both being normal, right? What do you know about this joint then? What do you know about the joint distribution of x and y? What can you say about it? Any? If x given y and y given x are both normal, what can you say about the joint? Does it exist?
Nothing.
Right, exactly nothing. It might not exist. It might not be normal. It could be normal, but in a very particular situation, right? So all of a sudden, you see, instead of me talking about a joint normal distribution and knowing what my parametrization is, if I start talking about those two conditionals, even for the simplest case, things start to fall apart, right? And that's precisely what spatial epidemiology has done. That's exactly what this is. They said, my graph is now described by these conditionals, by this autoregression of each variable given the rest. And now what they say is that, well, if I'm looking at a state given the other states, then all the states that are not neighbors with this state will disappear from my regression. So the corresponding regression coefficients will be set to 0, right? So that's fine. That is a way to say, fine, I got my graph in my joint distribution specified by these conditionals. But then they realized, and that started with Julian Bisak's paper, then they realized, well, that joint distribution might not exist, right? So what they did then, they did a lot of work to somehow create parametrizations for these normal conditionals, such that they actually specify a proper joint multivariate normal distribution. And there's a lot of papers that just deal with this problem. It's a very hard problem, right? So in particular, here is an example of some results they came up with, right? So they start with this matrix W that expresses the edges of the graph, right? So this matrix W can have 0 or 1 elements, absence or presence of edges, or you can also take into account distances between centroids and argue that bigger states somehow are less related to each other because they are farther away and so on, right? So the point is this matrix W is fixed, right, and expresses the graph, right? So now, if I were to put all these conditionals together, what they did is say, well, I can only have 2 parameters, rho and tau, that express the variance of these regressions, right, all the same, just scaled up according to the fixed elements of the matrix W, and then a spatial autocorrelation parameter rho. So you see, so all of a sudden, see, I created a matrix DW here that lives in the correct space. It actually lives in the correct cone corresponding with my spatial graph, but depends only on 2 parameters. And even those 2 parameters must have other constraints relating, for example, to the minimum, maximum eigenvalues of the matrix W and so on, right? So they solved a very hard problem that should not have actually been needed to be solved to begin with. Because what we could do instead is work with the graphical model as it was specified by Dempster. And instead of moving from conditionals to joint distributions, which is hard, you can move from the joint distributions to conditionals, and then you'll have everything consistent and nice, and parameterized in a less restrictive manner. And that's precisely what I propose to do. It seems yeah, sure.
Parameterization, you have the variance is tau squared over Wi plus, right? So my understanding of that variance is that, for example, your state model, states that have lots of neighbors have lower variance. Is that correct? Am I interpreting that correctly?
Yes.
Because
right, Wi plus,
then
yeah.
the Wi plus will be large because it'll have lots of neighbors. So
right.
And then the variance.
So
the variance is sort of relative to how many neighbors you have. Right?
Yeah, which I mean I don't get it.
Right. No,
to be honest, I mean I'm just reporting.
Like,
yeah.
the assumptions
right.
in this parameterization. I think that's
right. They have to work things out because of this problem they had, But it's a problem that you didn't have to solve. Right. That's the point, and that's how pretty much papers have been written, with this problem, right? So now if we put together these 2 literatures, then hopefully we can create something more meaningful, more flexible, and hopefully that would give us better results. So if you read the spatial epidemiological literature, a complaint they have, a key complaint they have relates to over-smoothing. Right? So they complain that the fitted value, the fitted choropleth mass like this are too much smoothed out. So they somehow miss the important, the peaks of the posterior, right? Well, where does that constraint come from? Well, it comes from exactly this problem that they didn't actually have to solve, right? Okay, so what can we do about it? Well, we need to be Bayesian about it. We want to construct hierarchical Bayesian models that would take those dependencies into account and learn the dependencies we don't know. So we want to develop priors for our model parameters. And the key parameter is that precision matrix K, right? That must obey those graph constraints, right? So the G-Wishart distribution is conjugate to the multinomial. It has very nice properties, but some of these properties, however, are numerically not so trivial to obtain simply because of the presence of this normalizing constant of the G-Wishart distribution that is not so trivial to compute for any type of graph. But that problem has now been solved. Another problem that had to be solved relates to the dependencies that exist among the elements of K, right? So how to work with parameters that are variation independent? That's the problem, right? And the key solution to that is this double Cholesky decomposition. So now in this parameterization, CQ will be fixed because it comes exactly from D. D is fixed, right? And now the elements of psi are either free or constrained. If they are constrained, they are a deterministic function of the free elements. And the free elements are now actually variation independent. So that's nice. So you can actually vary them in any way you want, and you will obtain matrices K that are proper. They live in the right cone. So that's really nice. Now, in order to construct our hierarchical models, we need to be able to sample. So we need to know how to sample from this distribution, right? And that also has been the subject of quite a bit of research, right? So one method that has been proposed is the block-Gibbs sampler. You can think about the iterative proportional fitting algorithm for log linear model. You can think about the iterative proportional scaling algorithm for Gaussian graphical models. So they all relate to exponential families with cuts. And that's exactly what the Gibbs sampler is. So in order to make the block-Gibbs sampler work, you need to identify the cuts. In this particular case, the cuts are clicks in this graph. I showed you a click, that triangle that involves Floyd, right? So the determination of clicks is an NP-complete problem, right? So it's hard, but well, at least it has only need to be done once. However, even if you determine the clicks, you still need to invert matrices that are at the order of number of vertices in the graph minus the size of the minimum click. So that could get huge, because in our particular example, you would have to involve matrices of dimension 49 minus 3, that's 46, right? So if you want to think about even more areas, then your problem will be even more numerically difficult, right? So there are also these